Effective isotropic radiated power, known in short as EIRP, is the total power that a theoretical perfect omnidirectional antenna, that is an isotropic radiator, would need to emit in all directions to match the signal strength of your actual directional antenna in its main beam. In satellite communications, raw transmitter power doesn't tell the whole story. What matters to the satellite receiver or the ground station is the actual signal density it sees. By focusing RF energy into a tight beam, you can drastically increase the apparent power arriving at the target even if the transmitter output remains unchanged. EIRP is the combination of your transmitter's muscle and your antenna's focus minus the losses in the system. Thus, EIRP is equal to PT minus LC plus GA. PT, transmitter output power, usually expressed in decibels to a watt or decibels to a milliwatt. Feedline and connector losses in decibels. Antenna gain relative to an isotropic radiator. That's a radiator which radiates in all directions uniformly. That is mentioned in dBi. Say you are pushing 100 watt, that will be 20 dBW, through a linear amplifier into a highly directional antenna like a Moxon-Yagi hybrid with 10 dBi of forward gain. If you lose 1 dB in your coax and connectors, your EIRP calculation looks like this. EIRP is equal to 20 dBW minus 1 dB plus 10 dBi is equal to 29 dBW. Converting 29 decibel watts back to watts gives you a nearly 800 watts of effective radiated power. That extreme multiplier is exactly why a relatively modest ground station can successfully punch through the atmosphere and reach LEO, that is low Earth orbit satellites. Why EIRP is critical in satellite communications? Closing the link budget. To establish a reliable connection, the EIRP on the transmitting end must overcome free space path loss and atmospheric attenuation so that the signal arrives above